So let's use an example to help you understand the structure and also the dimension. It can be confusing if it's the first time you see it. So here is the handwritten digit data, image data. That's what we will do during the hands-on session. So the data contains 70,000 handwritten labeled image, digit image. We have 60 as training and 10,000, 60,000 as training and 10,000 as testing. So each image is a 28 by 28 pixel in grayscale. So you can see it as just a 28 by 28 matrix. So the data, how to transform the data, you need to, for feedforward neural network, you need to vectorize the data. So as I said, each image is a 20 by 28. Since it's grayscale, it only have one channel. It doesn't have red, blue, green. It only have one 28 by 28 matrix. Each pixel would be a number between 0 to 255. And then you vectorize this matrix by row, and then you can get this huge vector that's 28 multiplied 28. And also for the outcome, you need to transform, encode this outcome to be a dummy variable. So you will have your y will have 10 columns. Each column will indicate a specific digit from 0 to 9. So those are those things you need to do to pre-process the data. Let's look at a one hidden layer neural network example. Now, don't worry about this activation function, new activation function. We'll talk about that later. Here we use the activation function called ReLU. The function is RZ here. The function is very simple. It's basically just to learn, just to pick the maximum number between 0 to and Z. If Z larger than 0, it's Z 0 otherwise. So it's a very simple piecewise linear model. And we have input here. The input is all the digit pixels. You vectorize it. So you have 28 multiplied 28. That's 784. So that's all the input. That's a vector. And then you do linear combination. You get, and then you do linear combination, and you put activation function, this ReLU function, on top of the linear combination Z, and you get activated neuron A1, A4. So the first layer has 4 neurons, and then you do another round of linear combination, and you get this Z2 here, and we will connect Z2 to Y hat, and you need to apply activation function. Here we use softmax because it's the output layer, and we have more than 2 classes in this example, so we'll use softmax. You can see the softmax function actually transform the previous vector to be a vector with each value between 0 to 1. And then you can think of it as a probability of the sample belongs to each class. So here 0.66 is the biggest number, and it's corresponding to 4 position. It's on the 5th position since it starts from 0. So it corresponds to 4. So the prediction would be 4. That's how you get the prediction. And the loss function would be just entropy, since if you write all out, it will be yj log yj hat, and j need to go from 1 to 10. And since in this case yj would be 0 otherwise, so you end up only have y5 multiplied log y5 hat as the cost. That's what you want to optimize. And then in terms of the shape, here we have x input. The original input x is 28 by 28. That's a pixel. That's a black and white. If you have a color picture, you will have 28 by 28 usually by 3. So you have 3 different channels. And then you have 60,000 samples. So the shape of input x would be 60,000 and 28 by 28. And the shape of output y will be 60,000 and 10 column. As I said, each column will indicate each of the outcome 0 to 9, the digit. And we have 4 hidden units. So that's the structure of this one layer neural network. So in this case, vectorized case, the forward and backward propagation is for forward, you have input X, and you calculate Z, you calculate A, and then you have another round of linear combination. You have Z2, and you activate it, use softmax. And then you have A2, and you will get that cost function. The backward is the way you have to go from the cost and to update all the parameter, right? So you do derivative with respect to first A2, and then you do A2 to Z2. And then similarly, you can use chain rule to calculate dj with respect to dA1 just by dj derivative with respect to Z2 and Z2 to A1. And then you can go further from Z2 to W2 and B2, and you back propagate back to from Z2 to A1, and then you back propagate back to W1 and B1. And you need to cache those value I note here, because you will use this to calculate for next round of forward backward. So if you write everything out in its mathematical detail for this neural network we describe here with this 28 by 28 image, here is what you will get. And you can use this to basically build your neural network step by step from scratch by yourself. You don't need to use any built infrastructure, and you can try to build it by yourself. So the Z would be Z1 would be a 4 neuron, and we have 60 image. So the input X is 784 by, because after you vectorize it, it will be 784, and you have 60,000 image. That's the training data. And then in this case, the W, that's the weight matrix, would be 4 by 784. Because you have 4 neuron on the first layer, right? And then you have 4 bias type, that's 4 by 1. So you can get this Z. And then you apply the activation function, that's a ReLU. And you basically apply ReLU to each of the element of the matrix Z1. So you basically check each element and see if that specific value is larger than 0 or not. And then you get A1. And then you need to multiply the matrix W2 plus the bias term, you get Z2 and get A2 and get prediction. And then the derivative is the DZ. If you do the calculation, if you do the math behind it, you will see the form will be reduced to this simple and elegant format. Actually, J is the cost function. It just by default, it would be the cost function. So I didn't write DJ with respect to DZ here. I just put DZ here, but it will reduce to this elegant format of A2 minus Y, and then DW2 would be Z2 multiply A2 transpose, and you need to average over all M, and then all of this, it's the math format of the back propagation. You can see you go all the way and you calculate DW1, DB1, and DW2, DB2. That's what this for would be what you would use for updating the parameter. And here's the link. It's a Python notebook that goes through the infrastructure, this structure, this model here, step by step. You can load this notebook into Colab. If you use Colab, you can load it into Colab, or you can run it in your local Python too. Basically, this notebook, oops, we'll just let it load for a little while. But that notebook will go through each step of this, from reading the data and process the data and calculate all the forward and backward and update the parameter. So it will go through all of this step by step. So this will read, you can see this notebook will read in the image data that's here, and then it will scale the input this is initialize the parameter. And you define activation function. We will talk about that later, more of different activation function later. And you can see value function is actually extremely simple. You basically just get the maximum value of z1 and 0, and then you can return your result. It works extremely well. So that's beautiful. You define the loss and accuracy, compute cost. That's another function. You compute the cost. And the cost is also very easy to compute. And then you have forward propagation and backward propagation. We already write it out as in the slides. And basically, you just need to implement. Forward propagation is very straightforward. It's just a whole bunch of matrix multiplication. Backward propagation can be very complicated, depending how many layers you want to have, especially get to the form in this case. It's not that easy. You probably need some time to derive off this, but if you trust the result, that's the backward equation. And then you just basically implementing those equations in this simple case is not too bad. So it's basically most of this are matrix multiplication, but some of those is element wise. So you have to be careful about this difference here. This is matrix multiplication, this is element wise multiplication because of the value function. It's element-wise, activation function is element-wise. So you have element-wise multiplication here. But basically you implement backward propagation. You break it down to piece by piece. And then you start to update the parameter. That's the update parameter. You can see you calculate all the DW, and then you just update it by the previous W1 minus learning rate and multiply DW. And then you can start to optimize it. We also have different optimization method here in this notebook later that you can see how it's implemented, but we haven't talked about it yet. In real application, you probably won't write things out by yourself. It just help you to understand what's under the black box.